Hello and welcome to your second lesson on radioactivity revision. Today we are looking at energy levels in atoms. So there is a fill in the gaps sheet that you can watch, fill in the gaps whilst you go along. It is entirely optional, but it's there if you'd like it. That's on Google Classroom. And I'm just going to talk through photons and excitation and de-excitation and ionization and absorption and emission and all of that. Now it is not actually hard. I know people look back on this and think, ooh, it's hard in the sense that it doesn't really feature anywhere else in our specification. This was something that was put into the GCSE specification a few years ago, and it's like a snippet of A-level without really the explanation behind it or the ability to practice it. So I find it very frustrating. It's like almost teasing you with a bit, and then you have a lot of questions over it, but without going into the A-level spec, I can't answer it. But anyway, my point is, it's not too hard. You just need to learn it, basically. So let's start off. First bit. Electrons are arranged in energy levels around a nucleus. In chemistry, you call these shells. Electrons usually occupy the lowest possible energy level. It takes energy to move an electron up a level. And likewise, if an electron drops down a level, it gives out energy. Now, you can see in the diagram on the left there, two different diagrams. On the very left, you have a very traditional way of drawing energy levels even. So you can see number 1 is closest to the nucleus, 2, 3, 4, getting further away. On the right-hand side of that diagram, you will see a series of lines. N equals 1, N equals 2, N equals 3, etc. Now they are exactly the same. They are energy levels, but it's like they've done a little snippet here, and they've just looked between these lines, and they've then drawn it there. So if an electron is here, it's on energy level 1. Oh, goodness me, sorry. It's like it being there on energy level 1. It could jump to energy level 2, it could jump to energy level 3, and that would be like it jumping to 2 or jumping to 3. It's just another way of drawing it, basically, so just don't be surprised if you see either of them. Now, the next thing that people don't like is photons. Photons are effectively little packets, that's how we describe them, of energy or electromagnetic radiation. And we use them to describe light because light acts as a wave, and we know it acts as a wave because it does things that only waves can do. It reflects, it refracts, it diffracts. Particles do not do those things, and light does those things, so we know it's a wave. However, it also acts like a particle, and so we say it's got wave-particle duality. And again, we go a little bit more into that into A-level. So we think of light travelling as packets of energy called photons. The higher the frequency of the photon, the higher the energy of the photon. Now, in A-level, I know, I'm sorry, I keep talking about A-level, but you have an equation which is E equals hf. E is the energy of the photon, h is a constant called Planck's constant, and f is the frequency. So you can see that energy and frequency are proportional here. The higher the frequency, the higher the energy. So, as I say, you don't need that for GCSE, but I just thought you might find it interesting. So, if an electron absorbs a photon, it can move up an energy level. This is called excitation. The photon must be exactly the right amount of energy to excite an electron to a higher level. If a photon has enough energy, it can completely remove an electron and it ionizes the atom. Now, what I mean by it's got to have exactly the right amount of energy is, let's draw out these energy levels. So N equals 1. N equals 2. Why did I forgot how to write N equals 3? N equals 3. Right, here's some energy levels. And you have an electron chilling on energy level 1. Now, it may take, I'm making these numbers up because actually the energy that it would take is not measured in joules, it's measured in something called mega electron volts, which just gets a bit confusing. So let's say it takes 2.4 joules for an electron must absorb in order for it to jump from energy level 1 to energy level 2. It might take 1.3 joules to go from energy level 2 to energy level 3. Now, if a photon comes in, here's my, in fact, let's not draw that as that. Oh, goodness sake. Okay, let's say a photon comes in and it has 2.4 joules. Fantastic, that's exactly the right amount of energy for the electron to jump up in energy level. That's perfect. However, it might not have 2.4 joules, it might have 2.7 joules. Now I know it sounds a bit odd, but that is too much. It must have 2.4. If it doesn't have 2.4, it does not go up in energy level. And that photon will pass straight through. However, it could have 3.7 joules. Now notice 2.4 joules between N1 and N2, 1.3 joules between N2 and N3. So this photon could be absorbed and get the electron to jump all the way up to energy level 3. But do you see, it's got to be exactly the right amount of energy, otherwise it does not work. So when an electron has absorbed a photon and jumped up an energy level or 2, we refer to it as being excited. Now, different colour photons contain different amounts of energy. White light is made up of different frequency photons. So here I've tried to show that. That's meant to point. Oh no, where's the arrow gone? I'm just trying to get it to point to the red thing. Fine, I'll delete this and I'll just draw. There you go. Red, the lowest frequency, contains the least energy. Violet, the highest frequency, contains the most energy. Fine. Here's an absorption spectrum, and you can see you've got the highest frequency energy photons on the left and the lowest frequency energy photons on the right. If you pass white light made of all colours through an element, so here I'm talking about an element which is a gas. It's a lot easier to pass light through gases than it is through solids, as you are well aware. The spectrum of light on the other side would have colours missing, the black lines. This is called the element's absorption spectrum. Now these black lines represent the photons that have been absorbed in order to excite the electrons in the element. So the light gets shone through, some of those photons absorbed, causing the electrons to jump up. The light on the other side is missing those photons, and that's what we see as black lines. So there you go, the black lines appear because that frequency of light has been absorbed by the element. This is because these frequency and colours are exact photon energies needed to excite the electrons to the next energy level. So that's absorption. Now let's think about emission. When an electron drops down an energy level, it gives off or emits a photon. Because the electrons can only give off photons of certain energies, as in, let's look at this, it could only give off a photon of 2.4 joules or 1.3 joules or 3.7. They're very restricted energies it could give off. The photons can only have certain frequencies. We can identify different elements in a gas by the frequencies of light it gives off. Now so that's pretty much it. I have realised that we haven't done de-excitation or ionisation, so I'm just going to add a little bit in here. So, ionisation, very professional title, I think we'll agree. Ionisation is when an electron absorbs a photon with enough energy to completely remove it. So rather than just jumping up an energy level, it actually flees the atom. There you go. That's pretty much it. Right, I think that's everything. Hope it makes sense. Please let me know if you need any other help, but otherwise I shall see you on Zoom later.